So, what if pretty much everything you learned in biology class about how your muscles work is, well, kind of wrong? Today, we're going to dig into a radical new theory that basically throws out that simple muscles are just pulleys model. It completely rewrites the rules for how we jump, how we run, how we move, and it's all based on some fascinating new research. Okay, let's get into it.
So to start us off, I want you to chew on a question that sounds completely backward. What if the very muscle that's supposed to bend your knee is actually the secret weapon to powerfully straightening it when you leap into the air? I know, it sounds impossible, doesn't it? But that is the exact mystery we are going to solve today.
For decades, right, the textbook model has been super simple. Muscles are little engines, they pull on our bones, and that creates a twisting force called torque. Easy enough. But this nice, clean model has a huge blind spot. It can't explain this really baffling reality that scientists call a functional paradox. And that's when muscles that are supposed to bend a joint, the flexors, somehow end up helping to extend it. According to the old textbook, that should just not happen.
And this, right here, brings us to a genuine muscle mystery. We're going to call it the case of the paradoxical push. And to solve it, we're going to have to look for clues in some pretty unexpected places. The main culprit in our little mystery is the hamstring. We all know it as a knee flexor, right? If you're standing up and you pull your heel back towards your butt, that's your hamstring doing all the work. So here's the million-dollar question. How on earth does that exact same muscle help you powerfully extend your knee when you jump or push up from a deep squat? The old models just have no answer. Okay, so to crack this case, we have to follow the evidence. And our first clue forces us to look somewhere else entirely, the calf muscle. Yeah, the calf. This new theory says we've been thinking about the calf all wrong. It's not just a simple puller, it's way more sophisticated than that.
The key idea here is something called a muscular hydrostat. Now, that sounds super complicated, I know, but you've definitely seen this before. Just think of an octopus tentacle or an elephant's trunk. These things have zero bones. They move and generate incredible force just by pressurizing the fluid inside them. They change their shape, long, short, stiff, flexible, all with internal pressure.
And here's the big idea. Our calf muscle, specifically the gastrocnemius, acts just like one of these hydrostats. When you fire it up, it doesn't just pull on your heel. It squeezes inward, and because its volume can't change, it massively increases its own internal pressure. It literally self-pressurizes.
So what's the point of all this pressure? Well, it completely transforms your lower leg. Instead of being this kind of wobbly structure of muscle and bone, it becomes a super stiff, rigid pressure column. And this pressurization, it stabilizes both the knee and the ankle joints from the inside out, creating this incredibly solid foundation for force to travel through. That's clue number one.
All right, on to our second clue. This one shifts our focus away from the calf pressure and over to the hamstring's pull. Because it turns out, it's not just about what muscle is pulling, but how that pull gets redirected by the very shape of your leg.
Now, for any of this to work, there's one critical condition. Your foot has to be planted firmly on the ground. In the world of biomechanics, they call this a closed-chain system. It's a simple idea, but it's the one thing that changes absolutely everything about how forces move through your body.
So picture this. Your foot is fixed. The hamstrings contract, and they pull upward on the back of your lower leg. But since your foot can't move, the rigid geometry of your leg acts like a perfect pulley. It's like pulling a rope around a corner. That upward pull gets flawlessly redirected into a powerful forward and upward push that drives your knee straight. It's just brilliant physics.
So what this all means is that in this kind of system, a muscle's job isn't defined by its textbook label. The hamstring isn't just a flexor. Its action is totally determined by the structure of the leg in that boundary condition, the foot being on the ground. The geometry is king. It dictates the outcome.
Okay, so we've got our two big clues, the pressure column from the calf and the geometric lever from the hamstring. Now, it's time to bring them both together and finally solve the mystery. This is where the magic really happens, in this perfect partnership between pressure and geometry.
First, let's just imagine what would happen if you only used the geometry part without any pressure. If the hamstring pulls on a lower leg that isn't stiffened up, the whole system is wobbly. The force just squishes and deforms the soft tissues. It's kind of like trying to push water through a limp, floppy garden hose. Most of that energy just gets lost. You get almost no power out the other end.
But according to this new model, that is not what our body does. The very first thing that happens, step 1, is the calf muscle fires up. It creates that internal pressure we talked about and turns the lower leg into that rigid, non-squishable column. It's prepping the structure for the main event.
And this, right here, is the solution. Now, when the hamstring pulls, its force gets transmitted efficiently and almost without any loss right through that stiffened leg. That geometric redirection works perfectly, converting the pull into a massive push against the ground. The pressure from the calf makes the hamstring's job possible. That limp garden hose becomes a rigid, powerful pipe.
You know, the author of this theory, Seiji Sato, he sums it up perfectly. He says that the force you push into the ground isn't just one thing. It's the vector sum, or really just the combined result, of two different things working together. The pressure from the calf creating that stiff structure, and the geometric transmission of force from the hamstrings through that structure.
So this is a really cool explanation for a weird paradox, but why does it actually matter? Well, this isn't just some fun academic exercise. This model is proposing a whole new paradigm for how we understand and even train human movement.
I mean, let's just look at the real-world applications, because they're huge. In sports, this changes how you train. Instead of just focusing on raw strength, how hard can you pull, training might shift to the timing of pressure versus tension. Imagine a basketball player learning to stiffen their lower leg just fractions of a second before the hamstring fires for a jump. For rehabilitation, this is a game changer. Instead of just trying to strengthen a weak muscle by itself, a physical therapist could use specific postures to optimize the leg's geometry, or use things like compression sleeves to provide that pressure support externally, helping the whole system work better. And this might be the coolest part, robotics. This is basically a blueprint for the future. Imagine building these incredible soft robots that can self-pressurize to become rigid and powerful when they need to be, all without the heavy, clunky hydraulics we use today. It's biology-inspiring engineering. It's amazing.
So ultimately, what this model is really asking us to do is make a fundamental shift in our thinking. We need to move away from being muscle-centric, where we only think about which muscle is pulling, and move toward being structure-pressure-centric, where we understand that movement is this beautiful dance between the body's geometry and its ability to manage internal pressure.
So a muscle that's supposed to bend the knee actually helps to straighten it. Not because it's breaking the rules, but because it's part of this incredibly ingenious system of pressure and geometry that our textbooks are just now beginning to catch up with. It really just leaves us with one final big question. With ideas like this coming out, are we on the verge of a brand new revolution in how we understand human movement?